Okay, so yesterday we have discussed about common emitter configuration. Today we are going to start with common base configuration. So I guess this circuit you have already drawn yesterday? No, right? So please draw this common base configuration circuit. So the way we connect over here is base emitter normally is forward bias. So we connect positive to P and negative to N. Basically here the symbol, there is one difference. Okay. Yeah, arrow is missing. Please draw the structure. This is structure or a common base configuration. We have supply as VE. No need to draw board. This you can draw in exam if they ask you common base. Emitter current, collector current, base current, VBE, VCB. So two power supply we require, VE and VCC. Only draw the diagram, that's it. Rest leave it to me. Completed? Okay. Now yesterday you have drawn input and output characteristics in common base configuration, right? Now today we will explain why is the nature of the graph like that. Alright. Now this is my NPN transistor. The difference between the previous diagram and this diagram is earlier we have used the symbol, here we have used the structure. So tell me PN junction between base and emitter is forward bias or reverse bias? As per the supply, forward bias. And between base and collector, reverse bias clearly visible over here. Alright. So here we have written the description. So for BJT to use as an amplifier, you have to operate in the active region. And for active region, base emitter junction should be forward bias, base collector junction should be reverse bias. And which is the biggest current, terminal current in a BJT? Emitter current is equal to IC plus IP. Alright. So you have to see the behavior of common base mode in two characteristics, that is input and output. Now, what is input current in common base? IE. And what is input voltage? VBE, as you can see. So this is the way the input characteristics was, right? Now we are here to justify why it is so. Alright. IE versus VBE, so you can refer the characteristics which you have drawn for two different values of VCB, right? And we can see very clearly for same values of VBE, if I increase the value of VCB, my current IE increases, right? Correct? In common emitter, x-axis was same. What was y-axis in common emitter? IP. Yes or no? And that was in microamperes. This was in common emitter mode. But now in common base, it is emitter current. Okay? It is which characteristics is resembles? We have input as base and emitter, na? Instead of current IP, we have IE. But between base and emitter, we have PN junction only, na? See here. But base and emitter, what is connected? See here. PNN junction, na? And that is forward bias. So what will happen? As we go on increasing the voltage VBE, it will resemble the PN junction characteristics. That's why the nature of the graph is exponential. Did you understand this? Okay. Exponential nature is clear. Now I have to explain for the same value of VBE, why IE is higher for a higher value of VCB. Okay. So reason is written over here. So as VBE increases, what will happen? Your PN junction becomes more forward bias. Okay. So more carriers will reach the collector region as VCB is fixed. Alright. So therefore IE increases exponentially with VBE. That is what we have seen. Now, as VCB increases, the curve slightly shifts to the left hand side. Okay, that means at a higher value of VCB, why does the IE increases? That is what we are explaining right now. So the reason is as follows. As the collector base junction becomes more reverse bias. See, I'll again repeat whatever I've explained yesterday. So this is my emitter region. N. This is my base region, which is P. This is my collector region, N. Okay, this is collector, base, and emitter. Now, what are we saying? We are saying that a collector base junction is becoming more reverse bias. What is the consequence of that? The consequence is increase in the depletion layer over here, right? This depletion layer increases. Yes or no? So this is my depletion layer. It has increased. So width of the depletion layer increases. That means this width is increasing. Yes or no? Okay, this is my depletion layer. And what is the name of this depletion layer? Collector base depletion layer. Yes, no? Reverse bias, PN junction reverse bias, depletion region width increases. So less voltage is required to forward bias base emitter junction. How is that possible? Why we say when the width is increasing, less voltage is required to forward bias the base emitter junction. How is that possible? How is that possible? See here. Can you see this is my base region now? Whatever I'm marking in this. This is my base width W. If W is reducing, I mean base region earlier was full. Now due to increase in the reverse bias, base region is becoming thinner and thinner. If base region is thinner and thinner, whatever VB you applied over here, let's say VBB, VB, whatever you applied over here was like this. Okay. Earlier, the graph of VB versus IB was like this. So for one value over here, let's say at 0.7, you were getting some current. But now what we are saying is, as depletion region is increasing, more carriers are flowing, right? At the same voltage. More carriers are flowing at the same voltage. So let's say here, for 0.7 volt VB, we were getting input current as how much? 20 microamperes. All right. Now, since the depletion layer is more at the collector base junction, base region is region width is less. All the carriers which are coming over here will recombine less because there are less number of holes now. So the carrier recombination will reduce. Due to that, what will happen? At the same voltage, let's say earlier, when the depletion region was was normal, this is what was happening. But now what will happen is, at 0.7 volts, you are getting 40 microamperes of current. Why increase in the current? Because depletion region is reduced, less number of recombinations, so more number of carriers will be start traveling towards the base region without recombining in the base. Are you following what I'm saying? So if they don't recombine with the base, this voltage 0.7 volts will be comparatively lesser. मतलब ये 0.6 volts में भी 20 microampere दे सकता है ना? अरे 0.7 में 40 आ रहा है तो 0.6 we can say that at a lesser value of EB you can get the same amount of current as without the depletion region bias. Are you understanding what I'm saying? So because of this, what is happening is for a smaller value of EB you get the same amount of current. That's why it is written less voltage is required to forward bias the base emitter junction. Did you understand this point? Yes, no? Yeah. Without nothing happening at 0.7 you got 20 microamperes. Now the base region has become less, so number of carriers coming into the base, there are less recombinations with the holes, so more current is flowing into the collector region. So at the same voltage 0.7 volts VBE, 40 microampere is flowing now. Now if I reduce that 40 to 20, it will be available at a lesser VBE, right? That is what is the funda. That is why as you increase the value of VPE, what will happen eventually is collector base junction becomes more reverse bias. अब ये कैसे हुआ? Why this has happened? Yesterday we have written a VCE is equal to VCB minus V. What we have written? Tell me. One equation we have written, na? What was that? VCB or a VBC? VBC, right? Is what? VPE minus VC, ऐसे ना? Was this the equation? This is what the equation was, right? So here, this is my VDC. VCB, we have kept output constant, okay, at VCB. All right. So now, if I increase the value of VB, what should increase? VBC. Obviously, right? So that's why by increasing VB, your collector base junction become more reverse bias. So that point is covered. Now this point is clear. Less voltage is required to power bias the base emitter junction. That's why this curve shifts a little left. That's why at a higher value of VCB, your emitter current is even higher. We have to explain that now at a higher value of VCB, because higher value of VCB means more reverse bias. More reverse bias means what? Less number of recombinants at the base. So less number of electrons will recombine at the base, more of them will flow to the collector, which will lead to a higher value of IE. Okay? Yes or no? Now, from the input characteristics, you can determine input impedance. Now, input impedance is voltage upon current. This case, the voltage is VB, but the current is delta IE. So wherever you have drawn the input characteristics, please write this equation. This is input impedance or input resistance of the device. Input resistance of the device is Rn, which is delta VB upon delta IE at a constant VCB. Okay, it's the slope of this graph, exponential curve. Because this slope is an, for a small segment, it can be a straight line, right? An exponential curve can be a straight line, correct? For a small segment, see, for year to year, it is a straight line. So with that, we determine the slope and we calculate the resistance. Written? Can we move on to the next point? Now listen very, very carefully. I think you have drawn this graph, right? Where the current IC is almost constant or parallel to the x-axis for different values of I. And you see they are ending towards the negative side. At -1, they are going down. So this yellow region is my saturation region, green is my cutoff, and region number 2, which I have written, it's my active region. Other than your yellow and this thing, your entire region is my active region. And where you want to operate your BJT for an amplifier in the active region. All right. So this you have already drawn. Only thing is you didn't know that BJT can be distinguished in these characteristics in 3 regions. So green is cutoff, yellow is saturation, and this wherever I've written 2 is my entire active region. Now I have to explain you why this characteristics is so. Okay. So region number 1 cutoff, active, then region number 2 is active, and region number 3 is saturation. Now, in active region, now where is my active region? This is my active region, right? Let me draw it over here. So my active region looks like this. This is VCB versus IC. So VCB versus IC. And how the characteristics is? Like this, straight line. Okay? So this is different values of I equal to 1 milliampere equal to 1.5 milliampere. Now we have to explain why it is constant. Okay? In active region, IC is constant due to constant VB. Now why VB is constant? Why does VB is constant? Because even for a small change in current, your VB graph is like this, right? Almost exponential. It's almost the variation in VB is very small. That's why we treat this as a constant. So IC is constant due to constant VB. Now, even if VCB increases, see, even if VCB is increasing, now VCB is increasing from 0 to 10, let's say 0, 1, 2, 3, so on and so forth till 10. Your IC is equal to alpha times I, right? Alpha, na? IC is equal to alpha times I. So alpha is almost less than, very, very close to 1. Alpha is around 0.99, say. So IC will be almost equal to IE, which is remaining almost constant. Now from the input characteristics, what did we do? Input characteristics kaise tha ye dekho? This way, right? It was this way, right? This was IE, correct? And this was VB. Now over here, let's say this is 0.7. So the corresponding value of collector emitter current will be, let's say, 1 milliampere. Now, if we increase this to 0.72, the current will be 2 milliamperes. That means for a small variation in VB, IE is increasing exponentially. That means when a VB voltage variation is very less, that's why it is a constant. Okay. So if my base collector junction is increasing, why is the IC constant now? Why is the IC constant? Why it is not increasing? Tell me. Again, I repeat, your VCB is my base collector junction, which is reverse bias, right? So I'm increasing this voltage more and more. So what is happening? VB is remaining constant. Now I'm increasing only base collector junction voltage. So what will happen now? I have explained you many times this same concept. Over here only. VB is fixed. Now I'm going on increasing the value of VBC. So what will happen now? No, VB increasing means what? More and more carriers will flow, right? Yes or no? Now I am increasing VBC. So what will happen now? More carriers won't flow. Only same number of carriers will flow, which was flowing with VB changing, which was there with VB constant value. So that many carriers will only flow. That's why your emitter current and your collector current are almost constant. We have a straight line from 0 to VCB. Even for 0 VCB, we are getting almost a constant current. Why? Because even if a base collector junction is 0 bias, still my base emitter junction is forward bias only. So if we have a forward bias base emitter junction and we are applying around 0.7 volts, my current will be constant only. That's the reason why the current remains constant in the active region. So over here, we can say the NPN BJT acts as a constant current source. It's acting as a constant current, na? So that's why it acts as a constant current source in this region, in active region. All right. And over here, output current is IC and input current is IE. So alpha, I told you, I give you the name for the alpha. Alpha is called as current gain in common base mode. So write this expression, please. Please note down this expression. Alpha is IC upon IE. Written. See, I guess some are still not understood the fact that why does the current remains constant. I'll explain that once. Now tell me, this is N, P, N. This is my collector, base, emitter. Okay. Now, यहाँ पे what is my input current? What is my input current? IE. What is my input voltage? VB. IE constant means what? अगर मेरा emitter current constant है at what value? At my value VB constant. Are you understanding? I can get the input current constant when I keep VB constant. समझ में आ रहा है what I'm saying? Array, this will be happening at 1. If IE is constant, VB will be constant only. Okay. So output graph means what? This is the output graph, right? Here we are keeping IE constant means VB is constant only. So VB is not changing. Now, listen carefully. So VB is constant. We have applied a fixed voltage. We are not changing it. Let me write it as 0.7. So at 0.7, my emitter current was, let's say, 1 milliampere. Now what we are saying, why does the IC doesn't increase, right? That is what we are saying. The IC is almost constant. So now base collector junction is reverse bias, right? How do you connect reverse bias? This is connected positive and this is negative. So this is reverse bias. So what will reverse bias do? There will be a increase in the depletion layer, right? As we go on increasing this VBC voltage, your depletion layer will go on increasing. So what will happen due to that? These carriers which are there over here in the N region, they'll go into the base region. Yes or no? So let me give some numbers. Let's say 1 lakh carriers are there inside the emitter region. Okay, and all those carriers, 1 lakh carriers are going into the base region. Base region में only 1000 volts are there. So 1 lakh, out of 1 lakh, only 1000 electrons can recombine with the holes. So some of the electrons will be lost, right? You cannot get more electrons now because ये fix हो गया. This VB is fixed. So out of 1 lakh electrons, few of them will recombine over here and a lesser number will reach at the collector, right? Because collector base junction is becoming more and more reverse bias. So इधर से carriers generate नहीं होंगे. These carriers will add up with this, that's it. Will join already existing over here. So we are not getting any additional carriers. In fact, the number of carriers are reducing at the collector side. And that is exactly what is happening over here. The collector current is almost constant. Almost means if I is milliampere, the collector current is 0.99, very, very close to each other. Okay, now did you understand? Why does the collector current remains almost constant? In fact, it's slightly less. अगर 1 lakh है ना तो 99,000 carriers have reached the collector and they are contributing the current flow. Only 1000 are recombined in the base. Okay, and that number is kept on reducing. If you increase more value of VBC, out of 1000, only 500 will be got at recombination at the base. That's why we say that the current remains almost constant. This you have understood why the current is almost constant now, at least. Yes, no, what? Yes, no, I agree. So in the emitter region, your I is 0, right? See here in the graph. In the emitter region, for I equal to 0 milliampere, below that graph, you get a cutoff region. So emitter current is 0. Yes or no? Yeah, emitter current is 0. So even if VC increases, IC remains almost constant at 0 milliamperes. As V is 0, I is 0, IC is almost equal to 0. But remember, base collector junction is reverse bias. Reverse bias में leakage current होता है. So that's why this leakage current is contributed due to minority charge carriers. As the collector base junction is reverse bias, only ICBO flows. Yesterday I've talked about ICEO and ICBO, right? So ICBO current is the reverse saturation current with emitter open. So IC is alpha times IE, that is an incomplete equation, it is plus ICBO. So even if IE is 0, IC equal to ICBO current flows. Are you understanding? So that's why in the cutoff region, there is some current, but that current is very, very small. So that is what I have seen shown over here in the green color. Even if I is 0, IC is not equal to 0, it is ICBO. All right? Yeah? Now, in saturation region, now listen carefully. What happens in saturation region? You start from here, okay? And then drastically the current reduces to 0. Why it happens? Why this happens over here? See here. I'll draw the characteristics in saturation. So this is my graph. VBC. Saturation region is what? From here, right? ऐसे है ना? It's only this region, right? So what are we saying over here? As my VCB is reducing from 0 to even lesser value, let's say this is -1. What will happen? As we reduce the value of VCB, that means it's becoming less reverse bias. Yes or no? So IC starts reducing. Why? Since as the reverse bias is reducing, electron have entered into the base from the emitter will be removed between the collector and the base. Okay, and will not be able to cross the collector region. See क्या कर रहे हो पता है? This base collector junction is becoming lesser reverse bias, meaning what? More recombinations will happen at the base terminal. Okay, lesser number of electrons will flow. Now at one point of time, this base collector junction will become forward bias. If this becomes forward bias, what will happen due to that? Now instead of these electrons going easily to the collector terminal, they will be repelled by this negative battery. Yes. So slowly, as you go on reducing the value of ECB below 0, the base collector junction will become forward bias and will not allow the current conduction to flow. So that's why your current drastically goes to 0 from a higher value as you decrease the value of VCB. All right. So that's why this is how the graph completely looks like this in common base configuration. VCB versus IC. Okay. In active region, the current is constant. In the cutoff region, the current is equal to the ICBO leakage current. And in saturation region, the current is drastically falling to zero because base collector junction is becoming forward bias. Ye dekho. VCB is becoming -1, right? Okay, collector base junction is becoming -1 over here, and base collector junction should be reverse bias, na? तो ये तो forward bias हो गया ना? So VC is what? +1. इसका मतलब forward bias. Yes, understanding? So this is all about your common base configuration. Okay, you have written the value of alpha. What is alpha? IC upon I. So please remember that, and it's called as common base current gain, and its value is very, very close to 1 because IC is lesser than I, but both are same almost. All right. Now let us go to common collector configuration. Here we have not drawn the characteristics. So common collector configuration, this diagram you must have drawn. Base collector, base collector and emitter. So basically collector terminal is common between input and output. And practically we connect the circuit like this. Between base and emitter and between collector and emitter. Listen, what is input and output side in common collector is? Input side we have IB, VCB. Output side we have IE and VCE. See here. Input side we have base current and VCB voltage. Output side we have emitter current and VCE voltage. So input characteristics is between VCB versus IB, and output characteristics is between VCE versus IE. Okay. Now first I'll explain output characteristics. So you have not drawn output characteristics of common collector configuration, right? So write down output characteristics IC versus VCE for a constant IB. Please draw the graph. IE versus VCE, emitter current versus collector to emitter voltage. Please draw these characteristics. I guess yesterday you have not drawn, right? Now for explanation, whatever explanation I have given for common emitter, output characteristics, the explanation remains the same. You know what is the difference? In common emitter, output characteristics, in y-axis we had IC instead of IE, and IE and IC are almost same. So whatever justification we give for output characteristics in common emitter, it remains the same over here. Okay, exactly the same. And that I've covered yesterday. And we just now we have discussed today that the collector current and emitter current are almost same. Okay, that's why the graph is also similar. Please draw the characteristics and refer to the explanation of common emitter output characteristics. I told you the difference. What is the difference? In the y-axis, instead of IC, we have IE. And IE and IC are almost same. Alpha times IE. Okay, drawn? Completed? Now, we go to input characteristics. Please draw the input characteristics. This is the last characteristics. Input is between VCB and IB for different values of VCE. Input characteristics of common collector configuration. Okay. Completed? Now I have to explain you all why is the nature of the graph like this. Drawn this? Okay. This is the same circuit which I have drawn over here in vertical manner. Now, here the question is, as we increase the value of VCB x-axis, your IB reduces by. As we increase the value of VCBC, is reducing, now it's going down. Why does the IB reduces? That is what we have to explain. Remember, we have kept VCE constant. Okay, can I start now? Explanation. Yeah. Completed? Okay. The question is, can you see that as I increase the value of VCB voltage, my IB is going down, reducing? We have to answer that question why. So listen carefully. VCE is VCB plus VB. Yes or no? No. Yes, no? So VB is normally fixed now. Why VB is fixed? So as I increase the value of VCE, VCB increases. Can I say that if this is fixed? Yes or no? So as VCB increases, bit of the base collector depletion region increases. Effective base width reduces. This we have done many times. That means bit base reduces over here. Okay. So the probability of recombination of electron hole pair in the base reduces. That's why the base current reduces. Okay, less number of recombinations happen at the base. That's why the base current reduces as you increase the value of VCB. Clear? So this was a clear explanation. VCB, why increasing VCB reduces IB? Because your base collector junction is region is becoming more, so effective base width is less. Less number of recombination means lesser IB current. Base current is less. Okay, and for fixed value of VCB, for a fixed value of VCB, yeah. Why does the IP, we have different, for different values of VCE, why does the graph is different? Why they are not same? That is what we are explaining here. For fixed value of VCB, what will happen over here? If VCE increases, VBE will increase, yes or no? If VCB is fixed, if we increase the value of VCE, VBE will increase, and if VBE increases, more number of electrons are put towards the emitter. Towards the region by the emitter, and if that happens, your base current will again increase. So that's the reason why your base current is slightly increasing for a higher value of VC. So these are the two justifications for the graph. All right. And with this, we complete common emitter, common base, common collector, configurations, input and output characteristics. So what type of questions can be asked? What are the different configurations in common emitter in BJT? Explain the input output characteristics. Or they can ask you directly, draw and explain input characteristics of a BJT in common emitter mode. Draw and explain output characteristics of BJT in common base mode. So there can be several types of questions over here. I have to still give you all questions for module number 4 and 5. I'll give it, I remember, I'll give it. Let me be a little more free, I'll give it to you. All right? Yeah, you can read about other things. Now, there is one thing which I want to cover now. See, in your syllabus, there are two terms written over here. One is operating point, one is DC biasing. So write down few points over here. DC biasing in BJT. Yeah, please write down. DC biasing in BJT. And what is the other topic? Operating point. Okay. So Write down what is BJT biasing. Write down the definition, or BJT DC biasing. Write down establishing and maintaining proper collector to emitter voltage and collector current, establishing and maintaining proper collector to emitter voltage and collector current in a BJT is called as BJT biasing. See, if this is my transistor symbol, where do you show IC collector current? Over here. Correct? Where do you show VCE? Over here. Oh, sorry. This is base terminal. This is collector terminal. This is emitter terminal. So, biasing means to bias the BJT so that it operates in the active region. और active region में operate करने के लिए it should be properly biased, and it will be possible only with IC and VC. Now this I will explain with the help of output characteristics. Have you drawn this much? Written this much? Okay. Now see carefully. Just tell me what is this characteristics? VCE versus IC. Okay. Just don't draw. Please don't draw. This is different values of IP. Okay. Now tell me the saturation region over here. So I'll draw this line. I'm explaining why we require biasing and what is Q point in one this thing only. Okay. Can you see this blue color dotted curve? The left hand side of this blue color dotted curve, I am calling it as 1. And one region number 1 is saturation region. Where is my active region? From here to here. Entire is my active region. Correct? Now if I want to operate my BJT as an amplifier, I have to bias it in the active region. So where is my active region? ये पूरा का पूरा active region है. This entirety is my active region. Whatever is there inside this trapezoid is my active region. Now, what is my Q point? Listen carefully. Let me draw it a little bigger. Okay. What is my Q point? Is see here. If we plot this line, and we have one more curve, let's say. This is IB. Okay. So, this red color graph is my output characteristics. This much you believe, right? What is this blue line? Blue line is called as DC load line. It has happened at one condition when you plot it, when you bias the circuit, the intersection of DC load line and output characteristics is my operating point. So I'm operating my BJT at this point, point A. And what is point A? Correspondingly, what is this value? VCQ at Q point. And this value is ICQ. So Q point is the optimum point where I'm guaranteeing that my BJT will operate in the active region only. This is my Q point. What is Q point now? How can I write it? Q point is VCQ, comma ICQ. See here, everyone. There are many points for VCE. There are many points for IC. But only those points which are under this, inside this yellow color box, only are valid for active region. And out of those box, at point number A, you get an optimum point, which is a Q point. An intersection of Q point, DC load line and output characteristic is my Q point. So mark this graph and mark the Q point, please, quickly. So the value of IC and VCE, which will make sure that BJT is operating with a fixed value of IC and VCE, it will operate in the active region, is called as operating point, Q point. So this is my Q point. Okay, Ron? I'll explain one circuit and I'll explain you how do we get that plot. Okay, that I'll do it on Saturday, but only draw the circuit and keep. This is completed. Please draw this biasing circuit. We'll study only one biasing circuit. This is the biasing circuit. VCC, RB, RC, and this is my transistor. Base, collector, emitter. For this circuit, we'll determine the Q point and plot that graph, ऐसे वाला, that Q point, okay? This we will do it on Saturday. I'll start with this and I complete LED and photodiode also on that day. This circuit name is fixed bias circuit. Only one needs to be covered, that's it. No numericals are there in this.